Chemical bonding 5, delocalization and resonance structures. The essential idea. Lewis structures show the electron domains in the valence shell and are used to predict molecular shapes. And the nature of science we'll have a think about, again, is that scientists use models as representations of the real world. In covalent substances, a localized electron pair in a bond is held in a specific position in the molecule, usually between two atoms in a single bond. You can see here, this shared electron pair has nowhere else to go. It is localized between the oxygen and the hydrogen atoms. There is no other place to put all the electron pairs in this structure. All the electron pairs are localized. In some covalent substances, an electron pair in a bond might be placed in different positions when you draw the structure. Neither of these structures above is accurate. Why not? Well, one of the electron pairs in the double bond actually spreads out over 3 atoms instead of 2. What? That's right. You can see here, this double bond has spread over all 3 atoms. When the electrons spread out, the structure is more stable. Delocalization of electrons within a covalent molecule happen when bonding electrons are in a double bond. They can spread out over 3 atoms or more within the same molecule. There is more than one possible position for a double bond in a molecule or polyatomic ion. Which structures contains delocalized electrons? Have a look below. Which ones of these 3 could contain delocalized electrons? What do you think? That's right, it's this one. And why is that? Well, the electrons in a double bond can spread out over all the atoms. When electrons are delocalized over several atoms within a covalent molecule or ion, several Lewis structures are drawn. For example, the nitrate ion. You can see these 3 representations. The double bond here, here, or here. All 3 exist. These are called resonance structures. The double-headed arrow is used to indicate that the true structure is a blend of all 3 structures. Sometimes this representation is used when delocalized electrons spread out. This suggests that all the nitrogen-oxygen bonds are the same in terms of bond length and bond energy. The nitrogen-oxygen bonds are all an intermediate type of bond between a single nitrogen-oxygen bond and a double nitrogen double bond oxygen bond. This style is not recommended for Lewis structures. You should draw the 3 resonance structures. Evidence for resonance structures. Let's have a look at ozone. We've got these 2 possibilities. The single oxygen-oxygen bond has a bond length of 0.148 nanometers and the bond enthalpy is 144. The double bond, oxygen-oxygen, has a bond length of 0.121. It's shorter than the single bond. And the bond enthalpy is far greater in the double bond than the single bond. But the bonds in ozone are actually, the bond length is 0.127, which is between these 2 numbers. And the bond enthalpy, again 364, is between these 2 numbers. So it is intermediate. You can see the bond order, it's 1.5, falling within 1 and 2 of the single and double bonds. Bond length measurements in ozone show both oxygen-oxygen bonds are the same. They are not 2 different bond lengths, as suggested by the Lewis structure. Instead, the oxygen-oxygen bond in ozone has an intermediate length and bond energy. It falls between a single and double oxygen-oxygen bond. Have a go at drawing the resonance structures for a carbonate ion and methanoate ion. Okay, do that now. Press pause. Now, do it. Okay. So you can see here, for the carbonate, the double bond here, here, and here. For the methanoate ions, we have the double bond between the carbon and the oxygen and the carbon and the oxygen. Obviously not between the carbon and the hydrogen, because hydrogen cannot hold that many electrons. So the delocalized electrons are found where? Obviously, they are found all over all four atoms, or the bonds between all four atoms in the carbonate ions. The oxygen is able to take those electrons. In the methanoate ions, it's over the carbon-oxygen bonds again, not the carbon-hydrogen bonds. Oops. And the carbon-oxygen bond lengths in each ions, well, all carbon-oxygen bonds have the same length in the intermediate between the single and the double bonds. Okay, let's have a close look at this methanoate ion, which forms resonance structures. Do you think that the methanoic acid also forms resonance structures? What do you reckon? Well, the methanoate ion, as we know, can, because the double bond can spread out over here. The resonance structures are shown here and here. Methanoic acid, the oxygen has two lone pairs, a bonding pair and a bonding pair. This could not spread over to here. So there's no resonance structures. The carbon double bond oxygen can't move. Oh. What about the carbon oxygen bond lengths in the methanoate ion and methanoic acid? Well, as you probably guessed, there's two different carbon oxygen bond lengths. The carbon single bond oxygen is longer and the carbon double bond oxygen is shorter in the methanoic acid, whereas in the methanoate ion only one carbon oxygen bond length is observed. Both carbon oxygen bonds are intermediate between the single and double carbon oxygen bonds due to resonance. Benzene, our good friend benzene. It's a very interesting molecule. Here we go. There's the two resonance structures you could draw. And obviously you will have seen it many times with the circle drawn in the middle. It's trigonal planar around each carbon atom with a 120-degree bond angle. So this bond there, 120. All carbon-carbon bond lengths are the same length, intermediate between a carbon-carbon single and a carbon-carbon double bond. The bond order of carbon-carbon bonds is 1.5. It's a flat hexagonal ring of carbon atoms. Here you can see a rather marvellous representation of it with a cloud of electrons above and a cloud of electrons below the hexagon of carbon atoms. Electrons are delocalized and they're spread out evenly across all 6 carbon atoms. They're not confined to those double bonds. And again, an equally marvellous representation where you can see this ring of electrons in a cloud above the hexagon, evenly spread out. So what properties of substances with delocalized electrons? What are the properties of substances with delocalized electrons? Well, they have intermediate bond lengths and bond strengths as compared to a single or double bond length between the same atoms. They have greater stability when electrons are delocalized. The electrons repel each other less. That's all for now.